In this video, we're going to take a look at section 8.4, which are some applications of radian measure. The first application we're going to look at is arc length. The second application will be area of a sector. And the third application will be angular velocity, angular and linear velocity. So arc length on a circle. From geometry, we know that the length of an arc on a circle is proportional to the central angle formed by the radii that intercept the arc. The length of arc of a complete circle is the circumference. So remember that back in geometry that you looked at the formula, circumference is equal to 2 times pi times r. So we're going to let s represent the arc length, and we can say that the arc length is equal to 2 times pi times r for the complete circle. And because 2 pi is the central angle in radians of the complete circle, the length of s of any arc with a central angle in radians is given by s, the arc length, equals the measurement of the angle in radians times the radius. So if we know the central angle in radians and the radius of a circle, we can always find the length of a circular arc. So our first example, find the length of arc on a circle of radius r equals 3 inches. So here's our circle, for which the central angle is pi over 6. So this one shows just the nice direct substitution into the formula. Arc length s is equal to pi over 6, the angle in radians, times 3. Cross cancel, 3 goes into 6 twice, and you get pi over 2. That's the exact answer. Then when you take pi divided by 2 on the calculator, you get about 1.57 inches. So this arc length right here is about 1.57 inches. So we want to take this idea of arc length and extend it to a couple of applications. The first application from homework is problem number 5. And it says a cam is in the shape of a circular sector as shown in the figure to the right. What is the perimeter of the cam? So if we're going to take a look at perimeter, remember perimeter is the distance around the outside of an object. We're going to add together these two values, which are both 1.845 inches, and then we need to also add the arc length. So the first thing we're going to do is find the arc length. Arc length is equal to the angle times the radius, but the angle has to be given in radians, and we're given our angle in degrees. So remember to convert, we take the angle measure, which is 165.59 degrees, and multiply it times pi over 180 to convert it to radians. So there's our new angle. It's going to be 165.59 degrees times pi over 180, and then times the radius. The radius is 1.845 inches. So we're going to put that in the calculator to find the arc length. So 165.59 times pi over 180, so I'll put parentheses, pi divided by 180, that's our measurement in radians, 2.89 about radians, times the radius of 1.845. So the arc length is about, let's see, we need to go to 3 decimal places, so I'm going to round this to, so the arc length itself is 5.3322. Then, to find the perimeter, we take that 5.3322 and add to it these other two sides. 2 times 1.845. So we're going to take our arc length and add it to 2 times the length of the radius, 1.845. And we get 9.022. All right, there's our first example. Next example for a circular sector. Let me move this back up. All right, next example. In traveling 3/4 of the way around a traffic circle, a car travels 0.226 miles. What is the radius of the traffic circle? So in this example, we're given the arc length of 0.226. So we know that this length of the arc is already 0.226. And we're given that the angle 3/4 of the way around, so we have to figure out 3/4 of the way around the circle. And then we're going to substitute the values that we know into the arc length formula. So arc length is equal to theta times the radius. So our arc length is 0.226 miles. That equals the angle, if we go 3/4 of the way around, 3/4 times 2 pi, or 3/4 of 2 pi, is 3 pi over 2. So there's our angle, 3 pi over 2 times the radius. So radius is what we're looking for. So multiply both sides by 2 over 3 pi to get rid of the fraction. So I get multiply both sides by 2 over 3 pi, multiply this side by 2 over 3 pi. We end up with the 3 pi over 2 canceling with the 2 over 3 pi. So R equals, I have to type this in the, let me type it in the calculator. So I want 2 parentheses 2 divided by, let's see, probably the best way to do this, just so we don't get confused, over 1, take 2 times 0.226, and we're going to divide that answer by 3 pi. And we just want to make sure that you have parentheses everywhere you need to, so your calculator does the right order of operations. So I'm going to do 2 times 0.226, and I've got parentheses around it because I want to multiply those together, and then divide by parentheses 3 pi. Put parentheses around that. Just make sure our order of operations. So the radius of the traffic circle in miles is nearest thousandth 0.05, tenths, hundredths, thousandths 0.048. All right, so that's our first application, our arc length. Next application is area of a sector of a circle. So this relates to the area of a circle. Another application of radians is finding area of a sector of a circle. Recall from geometry that areas of sectors are proportional to their central angles. The area of a circle is pi r squared from geometry, which can be written as a equals 1/2 times 2 pi times r squared. Because the angle for a complete circle is 2 pi, the area of any sector of a circle in terms of the radius and central angle is area equals 1/2 times the central angle times r squared when our angle is in radians. So you can see the picture up above. So we're finding the area of a sector. All right, first example. For an arc length S, area of sector A and central angle theta of a circle of radius r, find the indicated quantity for the given value. We're given a radius of 4.3, an angle of 2.4. I know it's in radians because it doesn't have a degree sign. Find A. All right, so A is going to equal 1/2 times the angle measure, which is 2.4, times r squared. The radius is 4.3 squared. Okay, so this one is a straightforward question where you plug in. So area is 1/2. I'm going to use 0.5 times 2.4 times 4.3 squared. Enter, we get 22.188, and we want round to the nearest integer. So 22.188 as the nearest integer is the nearest whole number. So that's about 22 centimeters squared. All right, next example for our area of a sector. A lawn sprinkler can water up to a distance of 40 feet. It turns through an angle of 145 degrees. What area can it water? So let's see, our lawn sprinkler can shoot out 40 feet. Here's the sprinkler. And it turns through an angle of 145 degrees. There's our 40 feet. And what we want to know is, what area can it water? So we're looking for the area of this sector. So we use the same formula. Area is equal to 1/2 times the angle times the radius squared. So this time our angle is given in degrees again, so we have to change degrees to radians. So area equals 1/2 times 145 degrees is radians. You can do 145 over 1 times pi over 180. That's our conversion from degrees to radians, times the radius of our sprinkler, which is 40 squared. All right, so let me see. If I multiply straight across, because I don't want to mess anything up, I get an area equals, I want to take 145 times pi times 40 squared in the numerator, just multiplying straight across, and the denominator I want 2 times 180. And I'm just going to put all of that in the calculator at the same time. So I'm going to put parentheses around the numerator, 145 times pi times 40 squared. Then I'm going to take that value, parentheses, divided by 2 times 180 is 360. If you put 2 times 180, you have to put parentheses around them in the bottom. And I get 2024, we want to 2 decimal places, 2024.58. All right, last application is called angular velocity. So the average velocity of a moving object v, any moving object, is the distance traveled, s, divided by the time elapsed, t. So remember, distance, rate times time equals distance. Okay, this is the velocity equals distance divided by time. Now, if you have an object moving in a circular path with a constant speed, the distance traveled is the length of the arc through which it moves. So it's an arc length, and that's why I've got an s. So angular velocity is the angle that it moves divided by t. So angular velocity is a measure of how many rotations, or angle measure, per time t. So you've heard angular velocity measured in units such as revolutions per minute, RPMs, radians per second, or rotations per second. The linear velocity is equal to, this is the linear, okay, so the angular velocity is how many rotations. The linear velocity is the speed of an object traveling around the outside of a circle. So the linear velocity is the angular velocity times the radius r. Okay? So how does all this work? Let's take a look at the first problem. You've got a turbine fan blade of a turbojet engine is 2.8 meters in diameter and rotates at 400 revolutions per second. How fast is the tip of the blade moving? So this tells us our angular speed. It's moving at 400 rotations per second. So what is that actual distance or the angle measure that it's traveling? Okay, so one rotation, remember that one rotation all the way around is 2 pi. So if we're traveling at 400 rotations or revolutions per second, then the angle measure is 400 times 2 pi, which is 800 pi. That's the angle per second. Okay? So the linear speed is equal to the angular speed, 800 pi per second, per 1 second, times the radius. And the radius is, the fan blade is 2.8 meters in diameter. That's all the way across. So half of that would be 1.4. Okay. So we've got the velocity is equal to the angular speed times the radius. So we get 800 times pi times 1.4 equals 3518, round to the nearest 10. So 3518 rounded to the nearest 10, we would round up to 3520 miles per second, or meters per second. All right, last example. All right, our last example, we have a blade on a typical saw rotates at 3,000 revolutions per minute. Calculate the linear velocity in miles per hour of one of the teeth at the edge of the 11-inch diameter blade. Okay, so we have a blade with an 11-inch diameter. So that means that the radius is 5.5 inches. So we want to figure out the angular speed first. Okay, so we have 3,000 revolutions per minute. So going completely all the way around once is 2 pi. So 3,000 times 2 pi per minute is the angular. Then we're going to take that value times the radius. So we have a diameter of 11, so we're going to take that value times 5.5 inches. So now this will tell us inches per minute, okay? And then we're going to have to convert that to miles per hour. So I think we probably might as well just do that. All right, so how do we convert inches per minute to miles per hour? Well, let me go ahead and I'm going to leave it like this. I'm going to put it as 3,000 times 2 pi, 3,000 times 2 times 5.5. I just want to make it a little bit smaller numbers here. So 3,000 times 2 times 5.5. So in the numerator, I've got 33,000 pi inches per minute. So now I want to convert that to miles per hour. So I know that there are 60 minutes in 1 hour. So I'm going to multiply that by 60 minutes over 1 hour. How do I know to put 60 over 1? I want the minutes to cancel. Now I need miles. So how many miles? 1 mile is how many inches. So I need to know how many inches there are in a mile. Well, I know that there are 12 inches equals 1 foot, and 5,280 feet equal 1 mile. So if I take 12 times 5,280, that gives me how many inches in a mile, which is 63,360. So now my conversion, I'm multiplying 33,000 times pi times 60. Minutes cancel. Let's see, inches cancel. And I'm going to be left with miles per hour. So I take 33,000 times pi times 60 and then divide that answer by 63,360 and I'll be left with miles per hour. So throw it in the calculator. You end up with, remember to put parentheses around the numerator, and you end up with 98.17 miles per hour. And we want to make sure that we round to the nearest tenth. So the nearest tenth would be 98.2.